right, we are going to talk about atomic structure today. What that means is the structure of the atom. Some of this you probably already know. I encourage you, when I put things on the screen, to write it in such a way that you understand it. So you don't necessarily need to recopy every word that I've written up here, but make sure that you have in your notes the information that we're discussing. I'm also going to add things around this, extra explanations, so that might be something that you need as well. The first thing we're going to focus on is the nucleus of the atom. And you might recall from yesterday, the nucleus is the small part in the center of the atom. So the nucleus is the central core of the atom. The second point says that the nucleus has all the mass. And I'm going to put a star by the word all. Would anybody like to tell me why I put a star, a really ugly star by the way, that's why I don't draw things, why I put a star next to the word all? It is important, but I actually am putting the star because it's not totally 100% true. For all intents and purposes, and in our discussions, this is how it is. In real life, however, is all 100% of the mass of an atom in the nucleus? The answer is no. The nucleus has most of the mass, 99.9999999999999% of the mass. But electrons do have a mass. It's just so small compared to protons and neutrons that are in the nucleus that we kind of don't count it. And so it has all the mass that we're going to talk about, but just keep in mind in real life that doesn't account for all 100% of the mass. It occupies very little volume. So even though it has lots of mass, the nucleus takes up very little space. So if I was to look at an atom on the whole, most of an atom is empty space. The nucleus is in the center, but around the nucleus, we know there are electrons, but it's not like they fill up all of the space that an atom is made up of. So most of an atom is empty space. Now, on this point here, empty space, I'd like to give you sort of an analogy to help explain how something could be solid if it's mostly empty space. Now, depending on maybe who your science teacher was last year, I know I used to show as many Bill Nye the Science Guy videos as I could in grade 9, and chances are if you had Mr. Samaka, he probably did the same thing. I don't know about the other teachers. But there's a part of one of the Bill Nye the Science Guy videos that gives a really good explanation about how something could be solid even though it's mostly empty space. If an atom was mostly empty space, and this desk is made out of atoms, shouldn't I be able to put my hand through it like it was a ghost? You would think so. But because there are electrons and the electrons are moving, that's what the quantum mechanics model said, the Bill Nye the Science Guy analogy was that of a spinning fan. So think of a fan like a ceiling fan or a floor fan that has blades that spin. Is the fan actually taking up the whole entire space, the whole entire circular space that it occupies? No, the blades are small and there's a bunch of empty space in between them. But when the fan is spinning, would you stick your hand through there? Probably not if you're smart and like all of your fingers. And so the idea is that, yes, it's mostly empty space, but because the electrons are moving around so quickly, it doesn't seem like it's empty space. In the nucleus, you will find protons and neutrons. Now, as a science person, I like formulas and abbreviations and symbols, and I have the habit of instead of writing proton, writing P with a little positive, and instead of writing neutron, writing an N with a little 0. You are welcome to do that, unless I was asking you to write some sort of formal report where you needed to use the word proton. If it's something I'm asking you on a test and you want to tell me that there's a proton somewhere, go ahead, use the symbolic representation. I know what it means, and now you do too. The last point there is that in the nucleus, different atoms have different numbers of protons. If I have the same atom, therefore, I should have the same number of protons. So I'm just going to write and vice versa at the end so that you know that the opposite is true as well. So that is what the nucleus of an atom is. It's the central core. It has all the mass. It occupies very little volume. Most of an atom is empty space. There are protons and neutrons, which you can represent symbolically, and different atoms have different numbers of protons. Vice versa is true. Same type of atom, same number of protons. Does anyone have any questions about the nucleus in general? Because we'll talk about each of the two particles, protons and neutrons, specifically. So maybe we'll zoom in a little bit here and go down. Protons, of course, are part of the nucleus. That's kind of repetitive, but I wanted to make sure everybody was clear that's where they are. Since they are part of the nucleus, remember the nucleus is where all of the mass is. Now, I'm not expecting you to know an exact value in grams or kilograms for the mass of a proton. What we're actually going to represent the mass of a proton with is something called AMU. It stands for Atomic Mass Unit. The particles that are in the nucleus have what we call 1 AMU as their mass. I could give you the mass in grams, but dealing with numbers like 1 times 10 to the power of negative 27 is cumbersome. An atomic mass unit is just a different way of measuring mass. So instead of writing kilograms, I'm writing AMU. It's just a different unit, and you'll see 1 is much easier to deal with than a big long decimal number. Now, protons have a positive charge. And you'll see that for protons and neutrons and electrons next week, I would expect you to know 3 things. The same 3 things. Where is it? What is its mass relatively? And what kind of charge does it have? Those 3 bits of information you would have to know for each of the subatomic particles. And then there'll be other details that are specific to them, but those 3 things I would expect you to know about all of them. Where is it? So I'll write this. Where is it? What is its mass? And what is its charge? Where is it? What is its mass? What is its charge? Those would be the 3 things that I would expect you to know about all of the subatomic particles. Now the third point is repeated so that I could clarify it a little bit more, talking specifically about protons. For me to know which element I have, I need to know how many protons there are in the nucleus. That means that the number of protons is the identification. If I ask you, what element is this, the only number that interests you is how many protons it has. So later on, once we talk about neutrons and electrons as well, you'll wind up with questions where there's lots of numbers given. But if I ask you what element something is, the only number that means anything is how many protons there are. So that is how you identify an atom. So you might ask, how will I know how many protons there are? You will look for the atomic number of an element, and it will be equal to the number of protons in the atoms of that element. So let's take a look at your periodic tables for a minute, so I can show you what we're talking about. Now, I mentioned this to everybody yesterday, but I'll just repeat myself. On your periodic table, there are a bunch of numbers in every single one of the boxes. The number that is on the top left-hand side, and it's even indicated that way on the key on your periodic table, that number is the atomic number of the element. So if I was talking about oxygen, whose symbol is O, its atomic number is 8, meaning that it has 8 protons. So we are going to talk about neutrons next. They are the other particle that you find in the nucleus. And so for neutrons, just like we did with protons, there are some things that you need to know. Thing 1, where is it? It is in the nucleus. Since we know that the nucleus is where the mass is, that gives us point number 2. Its mass is also 1 atomic mass unit. So the mass of a proton and the mass of a neutron are equivalent to each other. The third thing that you need to know is that neutrons have no charge. So those are the same 3 points I would expect you to know about a proton. Because they have no charge, that's why I write N with a little 0 as my symbol for a neutron. The 0 represents no charge. Now here's something that's different about neutrons as compared to protons. I can have 2 or more atoms with the same number of protons, but a different number of neutrons. So I could have 2 atoms of oxygen where one of them had, let's say, 8 neutrons and one of them had 9. They would still be oxygen because which element it is depends only on the protons. So neutrons can change in number, and you can still have the same element. If I have that case, if I have 2 atoms of the same element with the same number of protons, but they have different numbers of neutrons, I call them isotopes. Now I'll discuss isotopes in a little bit more detail with an example. But so I can tell you how many neutrons something has, I have to show you how to figure it out. The atomic mass, which on your periodic table is a number that's shown in every single box. The atomic mass for oxygen is 16, and it's the top right-hand corner. And again, there's a legend on your periodic table in case you forget which number the mass is. The atomic mass is the sum of the mass of the neutrons and protons in the nucleus. So, I could write a little formula. Atomic mass equals neutrons plus protons. Now that's great, except I usually wouldn't ask you to calculate the atomic mass because you could look it up on the periodic table. Normally the thing that I would actually be asking you to do is to figure out the number of neutrons. So we're going to rearrange that little math equation so that we can calculate neutrons instead. Neutrons will be atomic mass minus protons. So what I'd like to do before we talk about isotopes is go through a few examples of how to calculate the number of neutrons and some little details that you should know whenever you're doing this kind of a calculation. So I'm going to need a new screen for that. Is there anybody who has any questions about those 4 points about neutrons so far? So you will need your periodic table. You would be welcome to use a calculator if you want at this point. I think that most people can do subtraction without one, but if you wanted to use one, I wouldn't stop you from doing it. Does anybody need this screen to still be up? Okay. And don't worry about isotopes. We'll do isotopes afterwards. I just want to make sure up to this point right here, everyone's good. All right. So we'll come back to this and talk about isotopes, but we're going to take a second and talk about neutrons and how to calculate them. So we're going to pick a few elements. We are going to pick magnesium first, then lithium, and I'm going to do these two for you, and then I'm going to give you a couple more to do yourself. Magnesium, if you look on the periodic table, is number 12. Lithium on your periodic table is number 3, just so you have an idea. They're both on the left-hand side. If I'd like to know how many neutrons magnesium has, I'm going to do atomic mass minus protons. So for magnesium, its atomic mass, as written on your periodic table, is 24.31. And before I do anything, I'm going to change that number. The reason is, can I have 0.31 of a neutron? No, that's kind of ridiculous. So I'm always going to round that number to the nearest whole number. Sometimes I might round down, sometimes I might round up. In this case, instead of 24.31, I'm just going to write 24. That's the rounded off mass. And I'm going to subtract the number of protons. Now I knew there were 12 protons because magnesium is number 12 on the periodic table. This tells me there are 12 neutrons in magnesium. And sometimes, especially for elements at the top of the periodic table, you'll find that protons and neutrons are actually the same number, but it's not always true. For example, in lithium, same formula. Neutrons will be atomic mass minus protons. I'll take a look. I'll find that lithium's molar mass is actually 6.94, but I'll round that up to 7. So you can round up or round down. The rules for rounding would suggest if the decimal is 0.5 or higher, you round up. Since I'm not requiring that you write the formula that you use, because if it was a formula, I would put it on a formula sheet, that makes no difference to me at all. What I'd be looking for is, in your answer, have you indicated to me what your answer refers to? Now here, 7 is the mass, and 3 is the number of protons, because lithium was number 3. So I would give my answer as 4 neutrons. Now when I'm giving my answer there, I would expect you to either write the word neutron or use the n with the 0 so that everyone is clear on what we're talking about. But in your actual steps, that doesn't matter to me. I'm only going to look for a unit at the end. So notice that the number of protons and neutrons were not the same here. And that's usually the case. Most of the elements on the periodic table have a different number of neutrons than the number of protons that they have. So let's do a couple more examples just for fun. Let's do borium, and let's do something else with a fun name, bismuth. So let's do BH and BI. Just in case you're having trouble finding them, I'll let you know that BH is number 107, and Bi is 83. So I'll show everybody how you would do these examples just to make sure that we're all on track. We'll start with borium. According to your periodic table, borium's mass is 264, and you don't even have to round it because it's already rounded off to a whole number. Since it was number 107, you would do 264 minus 107. That gives us, if I do math correctly, 157 neutrons. For bismuth, which is number 83, the first thing I would do is round off its molar mass. It says 208.98. I would round that off to 209. It's number 83. So I would do 209 minus 83. 209 minus 83. Someone just tell me what that is before I do the math incorrectly. 126, yeah? Thank you very much. So it's just a subtraction. The real key thing to remember is make sure that you've rounded that mass off correctly, because if you're off by 1, then your answer will end up being incorrect. Does anyone have any questions about finding the numbers of neutrons that they would like to ask? So we'll do one more thing in your notes, and that's talk about isotopes. So I'm going to go back to the screen that we were on. And we're going to talk about isotopes. Now, I already told you that isotopes have to do with neutrons. And as a repetition, so perhaps you might ask yourself, do I need to write that again? I probably just wrote it down. Atoms that have the same, or atoms of the same element that have different numbers of neutrons are called isotopes. I'm going to highlight things that are different and things that are the same. So what is different between isotopes? The number of neutrons that they have. Because we know now that neutrons are part of the mass of an atom, that means, oh my gosh, what is up with my spelling on this? That their atomic masses are different. So there's two things that are different, the number of neutrons and sort of, by consequence, their atomic mass. What is the same? They have the same number of protons. So they're still the same element. And I would ask you on a quiz or on a test, not just to tell me what's different between isotopes, but to tell me what is the same, because they definitely have this in common. They have the same number of protons. So I'm going to use the example of carbon-14 and carbon-12. At the bottom, I've written out what's going on, and on the left, there's a picture so that I can show you what's going on. This picture here is carbon-12. And the other one is carbon-14. Now, if you look at them, they look basically the same except for one key difference. If we were to count the little dots, and the dots are supposed to represent protons and neutrons, the red dots are representing protons. And you'll see that in both of them, there are 6 red dots. So that means in the nucleus of both of those atoms, both of those isotopes, there are 6 protons. That is the same. The white dots are supposed to represent neutrons. And you'll see that in carbon-12, if I count them, 1, 2, 3, 4, 5, 6, there are 6 neutrons, so it's the same as the number of protons. But in carbon-14, 1, 2, 3, 4, 5, 6, 7, 8, there are 8 neutrons. Now that's written down at the bottom as well, just with words. And anytime I'm drawing a diagram to explain something, if you're not one with the drawing, you can tell I didn't draw that myself. I used someone else's diagram that they already drew. You don't have to. If I want you to know how to draw a diagram, I will tell you. So for example, tomorrow we're going to talk about drawing diagrams of atoms to show electrons. Then you actually have to be able to draw it. But this is just a visual representation of something that I also said with words. Now the other thing that I need for you to understand, and this is something that you have to know how to use, is this symbolic representation. You'll notice for carbon-12 and carbon-14, on the left with the pictures, instead of writing the word, I wrote a little symbol. The number that's on the top represents the mass, and the number that's on the bottom is the atomic number, which basically is the number of protons. And this way of representing an atom is good anytime, not just when we're talking about isotopes. The mass goes on the top, the atomic number goes on the bottom. And so if I wanted to ask you about isotopes, I might just show you those two symbols and ask you what's going on. I might not actually write out the words carbon-14 and carbon-12. So an isotope is atoms of the same element that have different numbers of neutrons. Their atomic masses are different. They have the same number of protons, therefore they're still the same element. And my example there is carbon-14 and carbon-12. Is there anybody who has a question about any of the things that are on the screen about isotopes that they'd like to ask?